Dr. Tyler McFayden is a postdoctoral fellow at the University of North Carolina, Chapel Hill. Her work focuses on social communication profiles of autistic youth and sex differences in neurodevelopmental trajectories. She also works as a member of the IBIS group at UNC, studying neurobehavior in infants. These webinars are made possible thanks to generous donor support. If you'd like to contribute, please visit our website at autism.org. And now I will hand this off to our speaker, Dr. McFayden.
Hi, everyone. Thank you all so much for having me. I'm thrilled to be here. Today, I'm going to share with you all a little bit of our novel results discussing white matter and language and autism. Thank you again for that introduction, Denise. You can see here that this work is far from independent and has significant support from my co-authors and the IBIS network. I like to start presentations with thank yous and disclaimers because I feel like these often get lost towards the end, and if I'm running out of time, I want to make sure this goes mentioned. This work would not be possible without the significant funding from the National Institute of Health, as well as the Safari projects. And also, I want to just give two huge shout outs, one to Dr. Jessica Girault, who was my personal mentor for this project. She is phenomenal and has guided a lot of my work in this domain. And also Dr. Joshua Retson, who provided all of the statistical and analytical support for this project, which was a significant heavy lift. So huge shout outs to these two. And if there are any questions today that I cannot answer, I'm more than happy to go back to the drawing board of authors, get the answer, and report back, especially if it is a highly specific statistical question. I may need to pause and return. I also wanted to just put these up here briefly. This project is part of the IBIS network, the Infant Brain Imaging Study. If you'd like to know more information about IBIS, which takes place across the United States, you can scan the QR code on the left with your phone. The results discussed here are also available in a peer-reviewed paper in molecular psychiatry. And if you're interested in reading more about that paper or reading further statistical details, you can scan the QR code there on the right. Last caveat before getting into the details today, you're going to hear me use a few different terminologies, and I wanted to explain why I'm using a variety of these terms. So today you're going to hear me use terms like high likelihood, autistic, infants with autism spectrum disorder. I'm also going to use ASD probably. I do tend to intersperse both person first and identity first language. And this isn't an attempt for me to respect everyone's personal preferences, including autistic self-advocates' preference to use identity first, and also some parent preferences to use person first language. The phrase high likelihood, I also want to take especially a minute to define. This used to be called high risk when we're talking about infant samples. In this presentation, I use the term high likelihood or elevated likelihood as a genetic phrase, really indicating that there's a higher familial occurrence of a certain genetic possibility, in this case, an autism diagnosis. So this particular language, this high likelihood, is actually key to this work, as these findings I'll discuss here are from, again, the Infant Brain Imaging Study, which uses familial likelihood as a way to group infants before they receive a final diagnosis of 2 years. So all in all, I just want to acknowledge that I am approaching this work from a perspective of an allistic or a non-autistic researcher. So I do attempt to really approach this work with respect and respect for all preferences, gratitude for our participants, and an openness to feedback throughout. So who am I and why this topic? Again, I'm so pleased to be able to speak today. By training, I'm a clinical and developmental psychologist, and my primary focus is on autism spectrum disorders, as Denise introduced. I find language in particular to be the most fascinating part of development. For me, it's what makes us stand out as a species. And my portfolio of work spans work outside of autism as well. So I just wanted to mention my positionality and how I approach this work from this transdiagnostic or interdisciplinary approach. I'm particularly interested in this middle of this Venn diagram, this slightly rounded triangle of individuals who don't use a spoken modality to communicate. So this may include individuals on the autism spectrum who are minimally verbal or partially speaking. This may include neurotypical infants who are learning how to speak and are pre-verbal. This may also include individuals who are deaf or hard of hearing and use a sign-based language to communicate, such as ASL. So I find that little intersection to be really a unique way in which to gather more information about how language modality affects the brain and how the brain recursively affects language modalities. So today I'm going to be focusing on just that top circle of autism spectrum disorder, although a little bit of the neurotypical infants as well. So I have a very applied interest in understanding how language develops. However, a lot of this presentation will be a little bit more of a basic science work today. But first, some of this background of why this actually matters. Right now, when babies or toddlers are slow to develop language, if you're a parent yourself, if you've been in this camp, you might approach your pediatrician and say like, oh, they're a little bit slow with first words. We're not quite hitting our phrase speech. You know, we're at 24 months. What do you think about that? Most commonly, the advice that parents are receiving is to wait and see. And this isn't necessarily an ignorant response, but it more or less reflects the heterogeneous outcomes of language development. We have many kids who we wait and they catch up. They develop language, they speak in full sentences, they didn't really need intervention or support. Language is just slower in some kids than others. But in certain groups, such as youth who will later go on to receive a diagnosis of autism, this wait and see model, I think, is really failing our kids. We're waiting too long. We might be missing these sensitive windows for early intervention and also missing opportunities to introduce new ways of communication, such as alternative or augmentative communication. So again, although the work today is not directly going to answer this wait and see question, it serves as an important foundation for understanding how early we can see language phenotypes diverging from typical paths, but also might give us some insight into when these early windows of intervention may be most effective. And when considering early diagnostics for autism, parents and clinicians are often on the lookout for language delays as they're one of the earliest emerging endophenotypes of autism. They're a great behavioral indicator that something may be on a different developmental pathway. And interestingly, language delays are also more common in siblings of autistic youth, even without a diagnosis of autism themselves, again, otherwise referred to as high likelihood siblings. So language delays in high likelihood siblings occur in 3 to 4 times the rate of siblings of non-autistic children. These behavioral phenotypes are really critical for diagnostic decision-making. However, some studies have highlighted the importance of understanding neural circuitry of these phenotypes, as it may provide a more mechanistic power instead of relying on behavior alone. So the neural circuitry might also give us insight into the precursors of behaviors, and thus may be visible before the onset of behaviors. So one such approach for investigating this underlying neural circuitry is to focus on white matter. As someone who was not a brain person, okay, I came into this, I was not a brain person. I guess I'm technically a brain person now. The way that I literally remember white matter is that white matter is white. They named it appropriately. There's gray matter, which is kind of the external cortex, and then there's white matter, which is the portion of your brain that's myelinated, as you can see from the graphic on the left. So white matter is composed of fiber bundles that contain millions of axons. These axons connect to different brain regions and form functional circuits. You can see the axon there on the right. It's wrapped in myelin, those little sheaths that give white matter its characteristic white appearance. It's like a fatty lipid protein. So these white fatty lipid protein sheaths serve as electrical insulators, which preserves the signal transduction in the brain. So we want white matter. That means that our axons are protected. That means that it can transduce information and send electrical signal without issue or without damage. So we're focusing here on white matter because it's key to understanding how information is communicated throughout the brain. White matter can be measured in a variety of approaches, but today we're focusing on fractional anisotropy, or what I'm going to call FA, because fractional anisotropy is too much of a mouthful. And this is measured using MRI, often using an approach called diffusion tensor imaging, or DTI. You can see on the picture of the left is a little baby posing in a significantly large MRI machine, and the graphic on the right is describing what we consider as low anisotropy versus high anisotropy. FA, that value there, that picture on the right, is used to provide an index of the rapid maturation of fiber pathways in the brain, especially during the first 2 postnatal years. Higher FA, so more to the right of that picture, is usually found to relate to increased age and thought to reflect an increase in myelination, axon density, axon caliber, and overall fiber maturation. So if you think about it, as we age, our brains mature, fractional anisotropy gets higher, our axon density becomes more tightly packed, as you can see in that picture, and our brain communicates more effectively. There's more of that fatty lipid protein that helps communicate the messages more effectively without misfires, if we think of it that way. So white matter and autism has been studied I wouldn't say thoroughly, has been studied in this field. And it's actually one of the earliest neural differences observed in autism as early as 6 months of age. The graphic you're going to see on the right is from an article by Wolf and colleagues in 2012. And they observed higher FA values with slower growth rates in autistic toddlers compared to non-autistic toddlers. By 24 months or 2 years of age, the autistic infants had lower FA in almost all white matter tracts, so they're not as densely packed. These results suggested that differences in white matter microstructure may emerge rapidly as early as 6 months and also have meaningful behavioral implications specific to autism. White matter has been studied in autism with a few different behavioral lenses, including social cognition, behavioral control, repetitive interests, and sensory interests, all in different white matter fiber tracts. So if you're a brain person, the ones that have been studied in the past include the inter and intrafrontal white matter pathways, the genu, and the cerebellar pathways as well. If you're not a brain person, you can ignore that. What you'll notice here, if you're a language person, like I am, what's missing from that? Language. No work to date has mapped on white matter development to language, despite the fact that these are occurring really at the same time. Developmentally, we see language and white matter from 6 to 24 months are making huge gains. And so I think this is a really interesting developmental period to focus on because we see language taking off and we also see that rapid maturation of white matter pathways. So white matter and language has been studied in non-autistic groups in what we consider neurotypical development. So white matter microstructure has been related to general cognitive ability, motor skills, language, and visual reception in non-autistic toddlers, suggesting that white matter does serve an important role in emergent cognition via the organization of fiber tract microstructural properties. Specific to language, white matter fiber tract development has demonstrated links with expressive and receptive language. So expressive language, what you produce, receptive language, what you understand. In non-autistic toddlers, in the arcuate fasciculus and corpus callosum, in these situations, higher fractional anisotropy, higher FA, was related to higher language. So the more densely those axons are packed, the better insulated they are, the higher an individual's language was. So systematically evaluating the relationship between white matter microstructure and language in autism, I think is really imperative for understanding the underlying pathophysiology, but also informing language interventions. When we're thinking of this wait and see model, what would these results suggest is the appropriate time frame for intervening if that's necessary? So for my current study, the goal was to evaluate the longitudinal relationships between white matter and language in infants at high likelihood and low likelihood. Again, remember, this is as defined by having an older sibling at 6, 12, and 24 months. And our specific questions, first one is, which white matter structures are related to expressive and receptive language in these first 2 postnatal years? And 2, do these relationships between white matter and language over time differ as a function of likelihood group? And when do they start to differ? When do they start to diverge? Is it from the beginning? Is it 2 years? Is it somewhere in the middle? I've mentioned this a lot, but this project used data from the Infant Brain Imaging Study, or IBIS. This is a nationwide study that has sites at UNC, University of St. Louis, Washington, University of Washington in Seattle, and University of Minnesota. Did I forget? Yes, and Children's Hospital of Philadelphia, CHOP. This study tracks infants with older siblings, some with autism, some without, at 6, 12, and 24 months of age. And the infants who have older siblings who are neurotypical, again, are called low likelihood siblings because they are at a lower likelihood of being diagnosed. We know these rates are between 1% and 2% here in the US. And for infants with older autistic siblings, these infants are called higher likelihood, as they are at a greater likelihood of being diagnosed with autism due to family genetics at or around 10 to 20%, as we've evidenced in previous research. So as a result, the high likelihood or elevated likelihood samples are considered enriched for the potential autistic phenotype. We had 461 total participants, which is a number that I think is excellent for this work, can only get better. We should only add more. The primary samples here are the high likelihood infants who later went on to receive a diagnosis at 2 years. That's 70. We also included high likely infants who did not receive a diagnosis of autism at 2 years. That's 251. And low likelihood infants who did not receive a diagnosis of autism. That's 140. Those were considered our comparison samples. The measures we used is called the Mullen Scale of Early Learning. We used expressive and receptive age equivalents at 6, 12, and 24 months. For those of you unfamiliar with this measure, this is a standardized measure with a variety of prompts provided by the clinician to try to elicit some type of linguistic response or following directions. You might think, how well is my 6-month-old following directions provided by a clinician? It is age appropriate. So at 6 months, we're looking for things like what consonant sounds they're producing, what vowel sounds they're producing, whether they're doing raspberries, things like that. But the fact that it's standardized means that you can generate an age equivalent. So based on your infant's performance, they're performing at or around the age of 5 months, 12 months, 18 months. And we use age equivalents instead of T-scores, which are standard scores, to avoid floor effects, as this is pretty common in the autistic group. Our white matter tracts of interest, you can see that picture here. This is actual tracts derived from the IBIS study. So these individual lines are DTI images. So that means that this is a composite of all the brain scanned and the different tracts that we were able to actually map onto via MRI. And you can see there we included the bilateral arcuate fasciculus, the bilateral uncinate and inferior longitudinal fasciculus, as well as the genu, splenium, and corpus callosum, the CC. Again, from these tracts, FA values were obtained, and again, fractional anisotropy for brain people represents the degree of diffusion along the primary fiber orientation relative to the transverse diffusion. I'm getting into the results now. What's coming up is a big table. Don't panic. Just kidding. Analytic plan, then a big table. To model the relationship between white matter, microstructure, language, and time across groups, we used a linear mixed effect modeling. Fixed effects included the group, which group member you're a part of, high likelihood, low likelihood, positive or negative for autism, white matter microstructure, sex, and then we also included these piecewise linear estimates for time. So we had a linear estimate for 6 to 12 months and a linear estimate for 12 to 24 months. We also controlled for age visit, site, mother's education. We controlled for all of those relevant demographic variables. Let's see here. We included interactions between time and white matter, between group and white matter. We used an autoregressive correlation structure. Missing data was assumed missing at random with multiple imputations. We also included random effects, a random intercept for each participant, and a random slope for 2 piecewise linear time points. If you're not a stats person, don't worry about it. I think we did it appropriately. This has been peer reviewed, and this is a solid analytic approach. I myself didn't do this either. What I want you to pay attention to is the particular term of interest that we're looking at here is this interaction term between white matter and group, FA and group. The reason this is of interest to us, we thought it makes sense if you're thinking about this intuitively. White matter should go up with time. There should be a main effect of time. That makes sense. It matures with time. Language should also go up with time. There should be a main effect of time and a main effect of language. So we know there's going to be a main effect of white matter and of language. We know from our work that for the most part, autistic youth are slower to develop expressive and receptive skills than non-autistic youth. So we assumed there was going to also be a main effective group. There were going to be some differences in how these groups were developing speech. What we were interested in was this interaction. How diagnosis determines language development, how does that differ in the context of brain changes? That's what we were mostly interested in. How are these brain changes impacting certain groups and not others is another way of phrasing that. So this is this interaction term that I'm going to focus on the most when presenting you with this large table. So let's focus on expressive language first. Expressive language is the language that we are able to produce. It's what you're listening to right now, what's coming out of my mouth. And I'm going to see this blue square across the table. Again, here you're going to see what terms am I focusing on the left? I'm focusing on this group by white matter interaction term. You'll see I have elevated likelihood, not autistic, low likelihood, not autistic, by white matter. Our reference group in this case is the elevated likelihood positive for autism spectrum disorder. So that's why they're not in this table. You can see here, if you look just in the blue box for the asterisks, you'll see that the only asterisks we saw for both of these interaction terms was available in the right arcuate. So my takeaway from this table, you're going to see there were some main effects of time, there were some main effects of group, some interactions between time and group, as we would expect. But when considering all of the white matter tracks, all of the things that we were looking at, left, right, bilateral, the only one that emerged significantly interacting with group to predict language was the arcuate fasciculus. This is I think a better depiction of our data. So let me orient you to this graph really quickly. First, we have the FA values of the right arcuate on the x-axis on the bottom. Here we have the FA values. We have the expressive language age equivalent score on the y-axis. And then that's in months there. So 10 months, 20 months, 30 months, 40 months. We have the panels grouped by visit. So 6, 12, and 24 are at each of those age points. And the different colors correspond to the different elevated likelihood groups. In particular, I want you to pay attention to the red bars here. The red bars are our focus point. They are our high likelihood autistic sample. So at the 6-month visit right in here, it's actually really hard to tell. These kind of hang together really tightly. The two high likelihood groups really hang together. So the gray and the red bars are almost overlapping. High likelihood, whether you have a diagnosis or not, pretty similar. The blue bar, the low likelihood negative, kind of stands apart. It's kind of showing this no relationship pattern. By 12 months, the high likelihood negative group and the low likelihood negative group, those without autism diagnoses, are really starting to hang together, the blue and the gray. What we start to see is the high likelihood autistic group, those who later go on to receive a diagnosis, are starting to really parse out. They're really starting to break away from the other two groups at 12 months. And at 24 months, you can see this even better. There is no statistical difference between the blue and the gray groups here. They are statistically equivalent, but we can see here that the high likelihood autism group really has a quite distinct relationship between white matter and language than the other two groups do. So the other two groups are showing that generally there's a slight positive slope. The higher your FA is, the higher your language. This is most pronounced in the autistic group, where the relationship between language and FA is significantly, steeply positive. So we did kind of, let's see. Okay, so this is our actual data. This is what participants scored on. Their data points are their actual data. Here is what our model predictions looked like. Based on our statistical results, this is how our model predicts that people will perform. And really, again, we have the model predicted expressive language scores, we have the visit down here at the month, and we have the likelihood group indicated by these colors. This is grouped, instead of now by visit, by the amount of fractional anisotropy, grouped by the lowest third, middle third, and upper third. Basically saying, like, what percentile of FA are you scoring in? So again, we see very similar trajectories for the high likelihood negative and low likelihood negative across all 3 percentiles. It's really this high likelihood autistic group that's starting to break away, and in particular, the lower third FA percentile. Okay, so let's move on to receptive language. That was all expressive, how white matter contributes to the language that we can produce. Now, what about the language that we understand? You might think, well, this is going to be the same. We didn't know. Maybe it's going to be the same. Maybe it's going to be different. Again, we're focusing on these interaction terms here, and you'll see that we actually did not have any significant interactions emerge for any of the white matter tracts of interest. But I wanted to show you what these look like, because sometimes I think stats can be our friend. Other times, I think when we are too focused on finding statistical significance at an a priori of p is less than 0.05, we might miss something that is interesting. So go with me while I talk about the left and right arcuate fasciculus. I wanted to focus on these because this is what we found with expressive language, and so it was worth evaluating. You might be thinking, I've already seen this graph. You wouldn't necessarily be wrong. We see here the left and right arcuate fasciculus, left on the left, right on the right, almost the exact same patterns that we see for expressive language in the right arcuate fasciculus. You'll see that red group is really starting to break away at 12 months, and by 24 months, these are entirely distinct developmental pathways and relations between white matter and language. So even though this did not reach statistical significance level as determined by our a priori determinations, there's something here, there's something in the arcuate fasciculus, left and right, with receptive language that I think warrants further attention. So the summary here, this was a lot of brain, a lot of stats, a lot of information. So we saw significant relationships between the white matter arcuate fasciculus, FA, and language. No other white matter tracts emerge as significant. So all the ones that I mentioned in the introduction that we've seen that have linked to language, the cerebellum, the genu, the inferior longitudinal fasciculus, none of those emerged as significant for language. The cool part was we actually did the exact same statistical procedure, exact same one, except instead of relating white matter to language, we related white matter to a nonverbal intelligence component, NVI, something involving fine motor and visual reception. We didn't see anything significant in the fasciculus. So the arcuate fasciculus is unique to language. It is not just a general cognitive brain component. We're finding it specific to expressive and receptive language. And I think most importantly here, our takeaways, the relationship between language and the arcuate fasciculus was different in our autistic group compared to our non-autistic controls. So in autism, we saw a very strong positive relationship between white matter fractional anisotropy and language, which starts to emerge between 6 to 12. It remains clearly divergent by 24 months. And in non-autism, we saw white matter FA and language relationships are still significant. They're still positive. Higher FA means higher language, but it is of a smaller magnitude. And likely the high likelihood autistic infants with the least gains in FA values, remember that percentile, those thirds, exhibited the least gains in language over time and had the lowest language scores by 24 months. So we are seeing that, and particularly for autistic youth, this white matter maturation is either developing prior to, concurrently, or in response to lower overall language. What does this mean? What does this mean for us as parents, as clinicians, as researchers, as brain people, as stats people? I thought this was very interesting that the findings were specific to the right arcuate fasciculus. You see those brain images there on the right. That's what both sides look like, what we're able to image. So the arcuate fasciculus is this yellow band here. You can see this yellow band here. Most of the time, people think left language. For most individuals, the left side of the brain is lateralized and focuses primarily on language networks. So the fact that this was specific to the right side of the brain was interesting and not quite what we expected. We wondered that maybe these two regions were not homologous. We weren't able to fully resolve the arcuate on both sides. Just infant brains, y'all, they're super tiny. It's really hard to get really, really good high resolution imaging in infants. But we did control for this and statistically evaluate whether there were significant differences in the left and right in terms of homologous tractography, and there were none. So we're left to think maybe there is some evidence suggesting that left lateralization of language doesn't happen to the same extent in autism, which there is some research suggesting that. Or interestingly, could this reflect a more right dominant language process, such as prosody? A lot of work in autism has demonstrated that prosody differences do emerge in autism in early childhood. People often think about maybe there's a mechanical tone or low, not very much inflection. It sounds kind of robotic. So maybe this right arcuate is capturing something that is more prosodic in nature, not necessarily language knowledge. And then lastly, why only the arcuate? You know, it's so interesting when we're thinking about previous research. Other studies that have linked FA to language has found some evidence in the splenium, corpus callosum, across the same developmental period, excuse me, in non-autistic toddlers. But we did not find these findings even in our low likelihood sample, which are considered non-autistic toddlers. This, I think, could be due to differences in modeling. Our approach included multiple subject groups instead of a single typically developing group. And we also statistically predicted language development, including that like a change score. So the fact that this was longitudinal, we use a different modeling approach, could explain some of these differences. But all in all, I think our results suggest a level of specificity that other papers have not been able to speak to that generate links between language and the arcuate fasciculus specific to autism, which I think really could reflect the early specialization of this fiber pathway, specifically in autism. Where are we headed with this next? So our high likelihood autistic group really tended to like break away from the other two groups between 12 and 24 months of age. And I think investigations into a smaller time window, such as maybe 18 months, using denser developmental sampling, may actually elucidate some of these mechanisms and growth trajectories so we can fully understand the temporal aspects of this relationship. The IBIS team also plans to use longitudinal data collected through school age, which we are actively working on now and are almost complete with, to evaluate the persistence of this brain-behavior relationship, but also how much does this matter beyond age 2? There's so much else going on during this developmental period. What other factors are contributing to language skills or communication outcomes in school age? Let's see what else. And then I think, interestingly, further parsing the high likelihood autistic group by different language trajectories may also reveal more subtle differences in the language white matter endophenotype. So we have kids in the autistic group who are highly verbal, very verbally fluent, very verbally gifted. We have individuals in the high likelihood autistic group who would fall into the minimally verbal or partially verbal camp and who are not using more than 50 words spontaneously or flexibly. Could relationships between white matter and language differ as a function of those phenotypes? I strongly believe they could. So if you're sitting here listening, what are my takeaways here? Protracted development of white matter in infants who later go on to receive an autism diagnosis at 24 months is linked to lower expressive and receptive language. This is unique to the arcuate fasciculus. The arcuate fasciculus is a cool tract. It connects those two language areas in the brain, Broca's and Wernicke's. It's a direct connection to those two. So it makes sense that we found it here, but it's interesting that we didn't find it anywhere else. This relationship between white matter and language emerges and diverges in these groups as early as 12 months before any type of behavioral autism diagnoses are made. And these findings right now I want to echo, I think are in a basic science stage. We need more studies, we need more applications, we need more replications to understand how these findings inform our practice and detection for or direction to early intervention services. But I'll put a plug out there. I think these findings further underscore that wait and see is too late. You remember we saw this at around 12 months, clear divergence, wait and see to 2 or 3 years when SLP evals are being referred, 24 to 36 months. I think it's too late. So that's what I'll leave you with. I think this is exciting. I think this could be essentially a biomarker approach. I don't think we should put all infants in an MRI scanner, which is why I think this is still in the basic science stage, and we need to understand how to leverage this science to better understand our early detection models. But I think they're exciting findings nonetheless. Concluding again with acknowledgements, there are just so many people who have made significant contributions to this project, to the IBIS network, and projects that are ongoing. And I'm just so grateful that they've allowed me to enter this exciting group and study language. Thank you all so much for your time and attention. I look forward to answering questions in the Q&A function, so please put any there if you have them. I do believe that there are handouts available as well for this. And in the handouts, you'll see that I have included some supplementary slides with participant demographics, a little bit more data if you're interested in looking a little bit more there. I'm also happy to walk through those if needed. I'm pivoting to the Q&A.
All right, great.
Direct me.
Yeah, so if you click on the Q&A, it's down there at the bottom. You should see it. There also are, there's one question in the chat as well. So if you want to check that. And then if people want to type their questions into the Q&A now, it's a perfect time. And she's going to answer as many as she has time for.
I will. Okay. Let's see. I see the question from Chris, so that's what I'm going to address in the chat first. It says, hi, I thought autism was associated with too much white matter and too few very long right to left connections, but your study seems to suggest there is not enough white matter for language development. Is it later that there's too much white matter, too many connections occurs? ASD people seem to be overwhelmed easily by sensory stimulation. Chris, I think this is a very good question, and we hear a lot in autism about there's brain overgrowth, there's brain shrinkage, there's too many connections, we're not pruning enough connections, there aren't enough connections. And I think this is a very tricky thing to manage as well, because autism is a spectrum and you can have a variety of presentations. We have seen that there is head circumference overgrowth. The brains tend to be bigger, but this doesn't necessarily equate to more white matter. There could be more gray matter. There could be greater cortex volume. So generally speaking, I guess what this particular study didn't comment on was how much white matter you have, but it was the relationship between white matter growth and language. So infants who were having more white matter growth between 6 and 24 months were demonstrating more gains in language. So this would actually suggest that it was not, that overgrowth isn't a bad thing, that you need that white matter propagation, you need that development of those myelinated axons to develop language. So that's what these results would suggest. I don't think it can really address the sensory stimulation component, but there are a lot of other works out there that are talking about there not being enough pruning. There's, we're not being sensitive enough to, there's too much growth. So I think there is this balance between what's too much, what's not enough, what's fast growth, what's slow growth. Someone needs to write a great review about it because I think it's a lot to parse out. Okay, I'm turning to the Q&A. What Neomar asked, what is your opinion on the studies to indicate there's a reduced planum temporale is associated with greater language difficulties in people with ASD? I don't know if I can answer that question. I'd be really interested in reading some of that work. I'm not sure that I'm well versed in the planum temporale enough to connect that to today's work, but I'm going to make note of it, and I apologize that I can't answer that question. Daniel asked, let's see, I don't know if I can answer live. Okay. Daniel asked, ASD is a very broad label. Could this help create finer groupings? This is a really interesting question too, and I do think that there is something to using white matter to further categorize. Are there multiple autisms? It is a spectrum, as we know. There's a variety of heterogeneous outcomes within this. And I think instead of using white matter or language as relationship to create further groupings, I think it's probably best for us to just think of it as a continual spectrum like we think of as autism. I worry about parsing groups into further categories purely because this is just one dimension of functioning and doesn't reflect other elements of functioning as well that could be relative strengths or weaknesses. So I think this could help us understand a little bit more about functional development early on, but I'm not sure that I would use it to create groupings per se. Let's see, Gemma said, our daughter suffered a seizure and cardiac arrest at 2.5 months. She had myocarditis. She took medication for 6 months to get better, but since she has now been diagnosed with autism, could this experience have made her autistic? She's now 3 and has a twin sister who's not autistic. Yeah, Gemma, the causal questions, I'm not being your provider, not knowing your daughter, it's hard for me to answer those specific questions, but I will again turn you to this interaction between brain and environment. And there are many things that occur in our environment that impact the brain, many things that occur in our brain that impact environment. And this recursive connection, as I keep mentioning, I think people oftentimes forget that brain can also impact environment, vice versa. So there are certainly many things that neurodevelopment is this cascade and can occur and can contribute to the development of autism or any neurodevelopmental differences. If an MRI is planned, what should I ask for this detail from the imaging? That's a great question. From your perspective as parents, I would ask for the images from your MRI scan. This is, I think, commonly done as a thank you for participating. Right now, it's hard. We don't have this level of precision neuroscience or precision medicine to be able to say, oh, your daughter has 5. Factional anisotropy 5. I think that's hard to pinpoint, but if you ever get the opportunity to have repeated MRI measures for research or for clinical purposes, I think tracking that type of growth via imaging will be really important, and keeping the imaging as well so that providers can read that image. I'm not an equipped provider to read or interpret an MRI scan, but I think having some of this information longitudinally would be most effective for an individual, for a family. Alejandro asked, could you please talk about this findings when applied to premature babies, since the development of white matter and language are age-related? We have a son with very much delayed talking, eventually catch up, today teaches ESL and has multiple academic diplomas. His brother is profound autistic. It's very powerful hearing everyone's personal connections to this topic. I actually did recently produce a peer-reviewed publication that looked at extremely preterm, low gestational age newborns who are at an elevated risk of developing autism, about 7 times higher than the typical population. And this is, as you mentioned, because neurodevelopment is disrupted when a baby is born extremely prematurely. So we like to think that we have evidence suggesting that many individuals who are born extremely premature or low gestational weight make significant gains and significant strides and are not detectable, not differentiable from their full-term peers. However, for some youth, for some babies who are born premature who might have a lot of complications or oxygen deprivation, this can impact white matter development and all cortical and subcortical development, which can have cascading impacts. Let's see. I'm not sure I'm going to be able to get to all these, so I'm going in chronological order, and Denise, interrupt me if I need to do it another way. Daniel asked, are there studies in the specific domain that are active at the moment that are seeking participants? Yes, the IBIS study is always enrolling. There is also IBIS counterparts that work specifically with individuals with Fragile X syndrome and Down syndrome. So if you have an infant who has an older sibling, that's the requirement. It can't be a singleton, or a firstborn. We are actively enrolling at all of those sites visible on the map: Children's Hospital of Philadelphia, UNC, Washington, Seattle, University of Washington, St. Louis, and University of Minnesota. We'd love to have you all join. Samaya said, what are your thoughts about kids who develop language and lose it over time? My son is 7. His speech was normal until about 2.5, and around 2.5, he started to lose language. At this moment, he is 7 and almost nonverbal. This is an excellent question, and one that we did not address here in the study looking at different language trajectories. Indeed, there is a subset of autistic youth who develop language seemingly typically and then experience that regression where they lose language. And I think that regressive component is really not very well understood in the literature or in our relation to brain imaging findings. So that would be a very interesting thing for us to focus on if we have a subsample in this group to understand how is their language developing, how is their brain developing in tandem, and what's happening at this regressive time point. Tabia, I'm sorry if I mispronounced your name. How can it be explained that some autistic people have great language but then become nonverbal when they are stressed? We see this often in adulthood, in autism in particular, but in other forms of neurodevelopmental differences in neurodiversity and also in psychopathology, where language abilities are intact, and when presented with a significantly stressful situation, the ability to speak seemingly vanishes. And I use that term as an autistic advocate, explain that to me, that it's not a resource that they have access to at that point. And that we tend to explain with a primarily behavioral explanation, that when your systems are overwhelmed, something's got to go. Your heart has to keep beating, your brain has to keep working, so language goes out the door because we're focusing on surviving. At the core, kind of basic fight or flight response. So it's one of those things that's not prioritized in that system. The system is prioritizing surviving that stress, persisting through stress, and they're going to use other resources that are less taxing in that moment. What would you recommend the focus would be in speech therapy for children who have ASD? What should we start with, and how should we introduce to parents? That's a question from Zael. You might hate this answer because it's so individualized. Where you should start is meeting the child where they are developmentally and scaffolded to a +1 approach. I always think of N+1, stats person, numbers person. Take where you are, you're in, add 1. We don't want to add 5. We don't want to add 10. We don't want to go back. So if kids are working on producing consonant sounds, ba, da, ka, work on some voiceless consonant sounds, m, k. If children have single words, they have mom, dad, dog, they have nothing more, work on building up that single word repertoire. If they have single words, but they're not yet creating phrases, we work on phrases. So, and I'm not an SLP, so I shouldn't taught my SLP knowledge, but I think it's really about meeting the child where they are, because starting with phrases, if you're not yet at single words, it's going to be a miss. Chris said one other one, if I may, of course. Do you find anything correlating for lower myelination? What might that be due to? Is it lower stimulation, a chemical issue interfering with the process? Some have suggested toxins of various sorts, or maybe inflammation from viruses. Neomar further commented, the neuroinflammation reported in autism together with the presence of antibodies against myelin basic protein can be associated with language disorders. This would have to be studied. Y'all are generating many great future research directions for me. So Chris, I think if I'm understanding your question correctly, which I believe Neomar spoke to, is about what about kids on that lower end of myelination? What's causing that lower degree of myelination? Is it concerningly low or just natural variability? I don't know if we know. Daniel asked, are you aware of many genetic markers that are able to predict FA scores? You know, I am so interested in the epigenetics timeframe. I do not believe that we have identified any SNPs or any specific genetics that are predictive of FA white matter maturation. We have identified several gene groups, specific SNPs or SNPs that contribute to surface area growth, cortical growth, and cortical thickness, but I am not familiar with the white matter fractional anisotropy specifically. Rosetta asked, did the study look at children who had language prior to their autism diagnosis, lost it, and regained some? Again, great question. I kind of answered it above that we did not look at children who had a language regression. I'm thinking back now, and I just think this is such a valuable part of studying is children who have a skill and then lose it. And I don't know if we had the sufficient sample size to do so. With our sample of 70 who ended up receiving an autism diagnosis, I'm not sure that there would have been enough that identified as a regression in language for us to focus on that. But wow, that would be so impactful for us to do in the future. Emily asked, when you say wait and see until 2-3 years old is too late, do you mean start with SLP IBI at 12 months or earlier? I don't know if we know when. I would like to enroll every infant in early intervention ASAP. Insurance would hate me. But I think when we wait, the hard part, again, with wait and see, I don't blame pediatricians, I don't blame providers, because a lot of kids, they develop bursts. They develop non-linearly. They're silent and then start speaking in full sentences. And I say that colloquially, but I also know that that is the case. True. There is true evidence for that. So, excuse me. For some kids, waiting might make sense, and for some kids, it might not. And I'm not sure how we figure out who are those kids, when does it make most sense to intervene, and what do we do? I'm working really hard to answer that question. The wait and see is like a career. That's like my career goal. Figuring out for whom does that work, for whom does it not? How long do we have to wait? Or should we just act before we even wait? Does that make sense? Should we act before we're waiting to see proactively? I think I answered. No, there's more. I think I answered. Okay. Emtil asked, I have a 9-month-old baby showing telltale signs of autism. Is it possible to increase growth of white matter at such age, and how? Wow, really, you all have such great questions. Also, I have a 9-month-old as well. So I know the developmental stages that you all are in. I don't know of any parenting strategies that are shown to increase or alter the developmental course of white matter growth per se, that are evidence-based. I would say to speak to any providers that you have about the concerns related to autism for your young child, continue to read to your child, sing to your child, and provide them with developmental opportunities for growth, as you would any 9-month-old baby. But I don't know if there's a specific way to increase or ensure that white matter myelination is occurring at an appropriate rate. It's hard to sit back and not know what to do. I understand that feeling very personally. Paula asked, the presentation and findings are very great, very interesting. What was the hardest part and best moments during this process? What a nice question. So I will say of the process of capturing this paper, distinct from the process of working with participants, the best part is always working with families. It's why I'm a clinical psychologist and not a biostatistician. It's because working with families is really the heart of what I do. It's really hard to get a baby in a scanner, though. Let me tell you, anyone who has a baby, it's hard to get a baby in a scanner. So that is a very challenging component. Of the paper itself, I would say imaging data is very messy. It's very large. It's hard to wrangle. And it's also very hard to make sense of it. So I think, we looked at 7 to 9 different tracts that were chosen based on previous research. There's so much else that you can do there with all these different brain areas and different ways of measuring brain. It's a lot to make decisions of, I'm going to do this one thing and why. So I think that's part of the challenge of doing this work, is what metrics are you going to focus on, why, and what are the ramifications there.